We're back. All right, back in my domain. Got the board, got my iPad. Wait for it, kids. Hank is still here. And boy, Hank, nice to see you. Yes, the gang's all here. Well, except for all of you, but other than that, at least I'm kind of teaching in my domain. Kind of feel so much happier. Okay, so the reason I kind of need to do this is that I need the board. I really need to be able to show you. This is kind of a demonstrative kind of thing. So let's kind of start with a quick review. So, I love teaching like this again. God, I wish you were over here. Okay, so let's quick review of current and magnetic fields. So let's say, for example, that the pin here represents the current in a wire. So if the current's going this way, I wrap my hands like this, and so if this was how it was going, I'd wrap my hands this direction. So let's say the current is going in that direction, okay? I'd have it like going like this. So the current, the magnetic field would be going into the page up here. So I'd put X's up here, and then it would be coming out of the page down here, and I'd put dots. So if the current was going in this direction, then I'd point my thumb in that direction. It would be coming out of the page on top. It would be going into the page down here. So I'd have X's down here. I'd have O's up there. Cool, lovely, no worries. So that's just a quick review. That's the simple right-hand rule. Now, where it gets more complex is then we're going to talk about charged particles moving in a magnetic field. So I've got this handy-dandy little equation. So this is the force created by a magnetic field, and it equals QVB sine theta. Okay? So let's talk about this. So this is going to be your charge. Okay? This isn't your heat calculation. This is your charge. This is your velocity. It's how fast it's going. This is the strength of the magnetic field in Teslas. And this is the angle between the velocity vector and the magnetic field. So, obviously, if you want a big force, you want this to be a 90-degree angle. If you have the sign of zero, that means there will be no force. So it's possible that you could have a charged particle moving in a magnetic field, but yet not feel any force if it's going parallel with the magnetic field. But if it's going at right angles to it, that's when you're going to get your maximum force. If you're at a 30-degree angle, obviously it's going to be somewhere in between. So here are your golden rules. If the charged particle isn't moving, like you have a static charge, it will feel no force because there is no velocity. Parallel equals peace. So if the velocity and your magnetic field vectors are parallel with each other, you won't have any interaction at all, and it will feel no force. If you have an angle other than 0 degrees, you're going to have a force. Obviously, the biggest one is going to be at 90 degrees. So much at home. Your maximum force is obviously going to be at 90 degrees. Now, this is where this turns into a convoluted thing. And forgive my drawing, but I teach physics, not art, so stay with me here. So this is what's known as the right-hand rule, and this is going to be important. So this is the right-hand rule for either velocity or current on a positive particle, okay? So it's either current or positive, like a proton, something like that, or a positively charged ion. You use the left-hand rule for negatively charged particles. So we're going to start with this one. So here's the deal. This is where this is a little bit more complicated than just a simple wire, but we'll get there. So you put your thumb in the direction of your velocity or the direction of the current, okay? Your index finger, looks like ET, your index finger points in the direction of the magnetic field, okay? So you got this action going. So this is like this physics kind of gang sign going, yo, QVB, sup. So you got this one going this way, you got the magnetic field going like this, and then these fingers here point in the direction of your force, okay? So you got thumb, magnetic field, force, like this, okay? We're good with that. So these are the three things. Your thumb, vector, your magnetic field, your force. Simple. So this is why and as you get into this whole thing kind of gets convoluted. So you got to have three things going on. If it's just a simple current, it's just boom, here you go, wrap your fingers, that's it. But when you have a moving particle, thumb, magnetic field, force. Thumb is your vector, this is your index, this is your magnetic field, this is the direction of the force. Okay, so let me kind of show you some examples. So imagine that you have a piece of paper like this, okay? So I got to view this from your perspective. So you've got a plane like this. So you're in a flat plane, okay? This is going to be important that you're in a flat plane like this. And you have a positively charged proton that's going in this direction. So imagine that we've shot a proton into the plane of this paper like this. So this proton is going like this. I've got a magnetic field, and this is an external magnetic field, going in this direction. So here's what I'm going to do. I'm going to point my thumb in the direction that the proton is going. I'm going to put my index finger in the direction of the magnetic field, which is like this, okay? And then what that means is that my force then is pointing downward. So what this would do, if this proton was coming in like this, it would force this proton down like this into a circular path as long as it was in that magnetic field. Okay? So you're like this with your thumb. The magnetic field is pointing into the page. So to actually draw this, what you would do is that you would put, if you were to draw this another way, what you could do is take your proton, show it going like this, and then you would have X's, okay? Which would indicate that the magnetic field, so your, oh, that gets screwed up. See, you forget the little things. So let me back up here. Oh, let me keep those. Here's your particle, and it's going like this. That way it matches with what we just dropped. So you've got a proton going like this, okay? Like this. You've got a magnetic field like this, so the force would be going down. So this is the other way that you could show it. The proton is going this direction. So like this, boom, points down. Now, the next logical question is, well, protons are kind of hard to come by. We do a lot more with electrons because they're easier to strip off and go out. So if it was an electron, okay, there's two ways that you can do this. It's a personal preference thing. One is that you figure out what's going to happen with the proton. So you go like this, you point down, oh, it's going to go like this, and then you think of it as an electron, it's just going to feel the opposite, and it would be forced upward like this. That's an option. Now, the other thing that you can do is what's known as the left-hand rule. It's a personal preference thing. So with the left-hand rule, oddly enough, you use your left hand. That's kind of clever. So you point your thumb in this direction. The magnetic field is going into the page, and then the force would be going upward. So I don't care how you think this through if it's an electron. If you want to do the left-hand rule and figure it out that way, fine, knock yourself out. If you want to do the right-hand rule and figure out what's going to happen with the right hand, and then you flip it over, I don't care. Doesn't make any difference. Okay. Now, so when you look at the actual force, so if I were to actually calculate this, and this is another way that you can define a Newton. So if you look at this QVB, so let's say that we've got a charge of 1 coulomb, okay, which would actually be a lot of charge. If you consider that each electron on each proton is like 1.6 times 10 to the negative 19th coulombs, to have this thing actually charged at 1 coulomb, that would be a lot of charge, okay? So if you have that 1 coulomb charged particle moving at 1 meter per second in a magnetic field of 1 Tesla, so you'd have 1 times 1 times 1, and everything is at a 90-degree angle, that is going to be generating a value of 1 Newton of force. So this is the other way that you can define a Newton of force. You could also say, hey, F equals ma, that's 1 kilogram being accelerated at 1 meter per second squared. That's the amount of force that you can feel that way. So now there's a different way that you can calculate force, QVB. Now, this is where this angle is important. So if you look at, if you were to put the magnetic field parallel with the force, excuse me, the magnetic field is parallel with the velocity vector, and you would be pointing like this, then there wouldn't be any force because they would be parallel with each other. So this only works when they're at some other angle other than 0 degrees. So that's the other way, that's the other visual that you can have. Okay. Now, let's talk about this one. So this is where this gets convoluted. This is why I got to be able to give this lecture like in this room. Okay. Shh. I'm not actually in the school. Okay. So imagine that you have a proton going like this in this direction. So now, instead of being in the plane of the paper like this, imagine now I've got this thing going in the plane of the whiteboard. Okay, so this thing is going in this direction, going like this, in this plane. The magnetic field is in the plane of the paper pointing down like this. So I've got a proton going like this and a magnetic field going like this. So what I'm going to do is I'm going to take my thumb, I'm going to point that in the direction of the positively charged particle, which direction. Then I've got to point my fingers, okay, or I got to point my thumb down in that direction. So I've got my positive particle going down like this. I've got my magnetic field going down like this. So what that means is that this is going to be coming out of the paper. Now, when you're answering questions about which direction this thing is going to go, be careful about saying, oh, it's going up or it's going down. So in this situation, if I were to say, hey, what's going to be the direction of the force? You would go like this, okay, boom. This thing is going to be pointing, the magnetic field is pointing down in the plane of the paper, but the force would be actually coming out of the paper at a right angle like this. Now, if you reverse the magnetic field and you pointed it up, then you would be going like this, okay? And you have a positive charged particle like this. The magnetic field, this is tough to do, would be pointing, hold on. Actually, hold on, give me 1 second. Hold on, I got to think this through. Something's jacked up here. That's it. Hold on. Let me start over. So, I lost track of where I am. So, if you got a positive charged particle going like this, okay, and the magnetic field is pointing down like this, it's actually going into the page. I screwed that up, okay? I wish I could go back and edit it, but it's live. And it's a Friday afternoon at 6 o'clock, and I've been going all day. So, you got this action. So, the magnetic field would be going down like this, okay? So that would be going in. Now, if the magnetic, this would be easier. So if the magnetic field is going up, then you point it like this, the magnetic field would be pointing up, and then it would be coming out of the page. So let me kind of undo, because I screwed that up the first time I went through this. So if you have a positively charged particle going like this, okay? I screwed up. Wish I could edit that, but I'm not going to. So you got this, the magnetic field is going down, it would be going into the page. If the magnetic field is going up, you're going like this, it would be pointing up, it would be coming, the force would be going out of the page. Now, if it's an electron, again, you can either use the left-hand rule or you can use the right-hand rule and flip it over, doesn't make any difference. My hand's all cramped up right now. Okay. Now, so let's say, and this is where we kind of combine different things. So let's say that you've got a wire carrying a current, okay, like this. So the wire's going like this, so you use the simple right-hand rule first. So the wire's going like this, you wrap your hands like this, that means that current is going to be coming out of the page, So up here, this is existing with dots, okay? And the magnetic field is going to be coming out of the page. Now, so then I've got a proton going like this, okay? So the proton's going in this direction. The magnetic field is coming out of the page like this, and my fingers are going to be pointing down. So if I shoot a proton close to this wire, this proton is going to get deflected downward. Now, here's the next logical question. Does this work out? What if we shoot it down here on the bottom side of the wire? So what if we have that proton down here on the bottom side of the wire, going in that same direction? Okay, that's a good question. So if we follow this thought process through, so I've got the wire going like this, so here's my current. On the bottom side, this would be subjected to a current going into the field. So imagine this thing's coming out like this in an arc. So then you would have X's like this. So now if you do the same thing again, so I've got my proton going like this, I've got my magnetic field pointing into the page, my fingers are going to point up. So it's still going to make that charged particle go closer to the wire. So no matter which side I shoot it on, I'm still going to get that positively charged particle getting closer to that edge. Okay. Let me see, got that. Got that. Okay, so now here we're going to combine some things. So let's say that, let me see if it's still here. I've lost my rubber stopper. Oh, that's horrible. Or use Al in a rubber band. Sorry, Al. Hopefully you don't go flying off. Okay. So here's Al, right? And so let's say that we're going to swing Al around in a circle like this. Now, if you all remember your circles in your circular motion, the direction of the force is always, and I know Liza would be all over this, she'd be over there going, oh, Mr. Burkett, I know this one, right? And she'd be going, oh, Mr. Burkett. It points inward at a right angle to the velocity vector. So visualize this. I've got a positively charged proton, oddly enough, moving in a circle like this, okay? And I'm going to have a magnetic field going into the page. Okay? Now, let's look at the force that that proton is going to be subjected to. So, again, here's the deal. I'm going to point my thumb in the direction that the velocity vector is going to point. Because remember, first law of inertia, this thing wants to move off in a straight line. So I'm going to point my thumb in that direction. I've got a magnetic field that's going into the page, so the force is acting inward. So that centripetal force created by that magnetic field is going to be acting inward. So now here's the cool thing about this. No matter where I go, okay, as I go around, that force is always going to be acting inward towards the center of the circle. No matter where I go, no matter where I am at this circle, this thing is going to be acting inward. Now, oddly enough, if this were an electron, and I wanted to make it move in a circle, then I'd still have to have the force acting inward. So then, if it was an electron, and the magnetic field would still be going in that inward, then the electron would have to be going in the opposite direction. Okay, because then if it were an electron and you use the left-hand rule, your velocity vector would be pointing down, your magnetic field would be pointing into the page, and then the force would be acting inward. So we take advantage of this to separate differently charged particles. So if you have the same magnetic field, if you know that in this situation, if the particles are moving in a counterclockwise direction, and they're in a circle, you know that they're positively charged. If they're moving in a clockwise direction, then you know that they are negatively charged particles in this external magnetic field. Now, the same thing is going to be true of anything. This only works if you're in a magnetic field. If you shut off that magnetic field, this particle is going to go flying off in a straight line. So you can only make charged particles move like this if they're in an external magnetic field. Neutrons, oddly enough, don't do this because they don't have any charge. So there's a couple of things that we can do with this. One option is that we can go, oh, centripetal force equals mv squared over r. Okay? Basic idea of centripetal force, mv squared over r. Now, that would have to equal the force from the magnetic field, which is going to be QVB. Now, so here's the deal. I left off the sine of 90 because these are always going to be at 90-degree angles. The sine of 90 degrees is 1. That's why we're not going to worry about that. Technically, the sine of 90 is there, but it's okay. Now, if you look at what happens here, I've got a velocity here and I've got a velocity here, so I can drop out one of those. So I've got mvr, otherwise known as momentum, so this is just the momentum, equals QB, and not the quarterback because we can't have sports right now. And so then, like for example, if you wanted to solve for R, you could have mv over QB. So if you know, like the mass of an electron, and you know how fast it's going, and you know its charge, 1.6 times 10 to the negative 19th, and you know the strength of the magnetic field, you can calculate the radius of that circle. Now, realistically, what they did is that they actually solved this for mass when they found the mass of an electron or the mass of a proton. So the charge they knew, the magnetic field strength, pretty easy to measure. You could measure how fast it was going, and you would measure the radius of like the cyclotron, which is what they would put this thing into. Then you solve for mass. So this equation is actually one way to find the mass of an electron or a proton, because obviously you can't take an electron, put it on a scale, and go, oh, well, there's the mass of the electron or the proton. No. So what you do is you start with this equation and you solve it for mass, and that's what allows us to figure that out. Now, here's another thing that you could do. Remembering that current is charge per unit of time. Now, if you look at the idea that if you have a circumference like the velocity is 2 pi r over t, okay, so remember something moving in a circle, right? This is just the circumference of the circle, how far it goes, divided by period, how long that takes, right? So if you solve this for t, and you would go, oh, well, period is 2 pi r over velocity. And then you could come in here and go, well, that's q divided by 2 pi r over v, which becomes qv over 2 pi r. Okay? Well, that's kind of cool. So then, this could be equal to your current. Okay, so there's another way that you can express current. Instead of charge over time, it's QV divided by 2 pi r over t. So that might be a good idea to keep in mind when you get to some of your problems. And there was one other thing. Now, if you look at, there it is, if you look at magnetic field strength, which is like mu naught I over 2 pi r, then you could also then, if it's a wire, you could put all of this stuff in here for your QV. If it's a circle, a hoop, remember that pi drops out and then it would just be over 2r. So you might keep that in mind. Also remember that velocity equals 2 pi r over t, but remember that period and frequency are inverses of each other. So you could write that as 2 pi r over 1 over f, which becomes 2 pi r frequency. Okay, so that's another cool thing to keep in mind. Okay, kids. Wow. So that was pretty intense. So hopefully that kind of makes sense. We'll expand more on this on Monday. Anyway, so that's the story. It's God, I wish you all were here. I really do. I miss this room. I miss the energy, oddly, the magnetism. Miss Tate talking to Noah and Mia giggling and Britton trying to not look at his laptop when I'm lecturing and keep him going, you know, kind of giving this look, you know, from the back row, and Eric trying to figure out, thinking about what he's going to write on the wall next, because he's really not focused on me. That's really what he's focused on. Anyway, Josh with his headphones, and anyway, I miss you all. I wish you were in this room. I love giving this lecture. It's a great lecture to give. Anyway, so yeah, feel the force, baby. Feel the force.